I spent over 20 frustrating years in the math classroom, but I did make two discoveries that give me hope. First, I took 10 math books from about grade 2 addition into algebra 2, and I figuratively tore out the pages that repeated earlier lessons. 10 books became just 2 books. We go over and over and over the same things, but we do it by memory. And so we don't understand, and so we forget, and so we never see the underlying patterns. Which brings up number 2. There are 9 underlying patterns to every common arithmetic and algebra problem. I call them actions because I added the how to the what. Instead of guessing from hundreds of forgotten possibilities, students can narrow down their next move to just one of 9 actions. We all know that an expert in any field is able to relate the new to the old by patterns. If we want to help the typical student and teacher succeed, then we need to teach patterns. And there are patterns. Let me share just a sample with you. What do decimals, denominators, place value, variables, and units have in common? Combine only like things. I will not prove to you why this is true. You will prove it to yourself. What is 3 dimes and 3 nickels? You said 45 cents, didn't you? You didn't say 6 dimes and you didn't say 6 nickels because neither of those is true. You converted both coins to the same coin, pennies. Then you added 30 plus 15. We add or subtract only like things because that is all we are able to do. Different things don't add up, pun intended. Another answer would be 6 coins. But here again, we converted the dimes and nickels to like or identical objects. Then we added. Now let's return to our original question. What do decimals, denominators, place value, variables, and units have in common? Decimal places must be lined up to keep tenths with tenths and hundredths with hundredths. Denominators must be made into a common denominator, so same things can be added. Place value must be lined up to add ones with ones and tens with tens. Variables, such as x with x, must be the same to be added. Units, as in the case of the dimes and nickels, must be the same before adding. These are all little things most of us teachers know, but have we seen their similarity? Have we explained the pattern to our students? Do they understand the real-life connection so they can feel it? By seeing the pattern, they start to get a sense of completeness that maybe they actually are understanding the rule and there's no more exceptions and other stuff waiting out there to grab them by the neck. Let's look at some specific examples. Notice in this problem how the ones, tens, hundreds, commas, and so forth are lined up. I can combine, which means add or subtract, plain numbers with plain numbers. They are the same kind, plain. Now see that not only are the place values lined up, but so are the things being combined. I'll talk more about the numbers and signs later. And my answer is the same kind of thing I added or subtracted. If I subtract fourths, then I get fourths. Everything to the right of the first number, on the right side of the orange dotted line, is the tag. The tag tells us what kind of things we are combining. All of the tag must match. If I try to combine 2 different things, like fourths and fifths or nickels or dimes, I can't. I have to stop and say there is no answer, or I need to convert them to something else, like 20ths. Again, miles cannot combine with yards unless I change one or both of them into the same thing or tag. I have these fractions written out in words to help prove the point. Combine same tags to get the same tag. Again, whether or not you know what an x minus 8 is, combine like things to get a like thing. That's all you need to know, that's all even a 3rd grader needs to know. Any kind of strange number, like scientific notation, obeys the action of combine only like things, COLT. Even though we rarely add percents when we do, they follow COLT. Now let's go back and look at some of these examples again to see how one simple process of combining will help students and teachers avoid their fear of negative numbers and make any curriculum more friendly and efficient. First, biggest number on top. Second, top sign to the answer sign. That means just copy it down. Number 3, it is a little different. Same signs add bigger, or different signs destroy smaller. Notice that the biggest number is on top. An invisible sign is always a plus, positive, or adding sign. Call it what you want. Notice the sign of the biggest number is the answer sign, always. Add the two numbers the normal way to get an answer bigger than the top number. Here is a regular subtracting problem. Everyone is already used to putting the biggest number on top. The invisible positive sign goes down to the answer. Now, because the signs of the numbers are different, subtract smaller to get an answer smaller than the top number. And by subtract, I mean regular, normal, old school subtraction that uses borrowing. Regular subtraction. This is what I mean by difference destroy smaller. Now we get to a weird looking example. Biggest number on top, copy the top sign down to the answer even though we don't know the number yet. Now look at both signs in the problem. They are different. Does not matter which is on top or bottom or what you call them. They look different, so do normal subtraction to get a smaller answer than the top. This example has one subtle change from the previous. Both signs in the problem are the same, so add bigger. Yes, this step is different than normal, where you look at only the bottom sign of the problem to figure out whether to do normal adding or normal subtracting. But, unlike the collection of rules and exceptions a student usually needs to memorize, this pattern holds up without exception for life. We have also eliminated the painful transition to negative numbers that most students go through. With this method, the typical third grader can combine any negative or positive numbers even before they understand what they are. Let's zoom out from those examples to briefly consider 3 practical principles that drive every step of every problem. They are in the orange boxes. COLT is part of first calculate complicated values. This is the standard order of operations, but worded in a way to give a reason. Its 4 actions point us to what and how. Notice that it is pretty much in reverse order of when we learned them. The second principle is change look but keep same value. When we sort, show hide, or substitute, all we are doing is changing the look of the problem to make it easier to solve. We are not changing the total value of the problem because that would be changing the problem itself. This principle is like an actor changing costumes to play a different role, but it is still the same actor. The third principle is value change needs counter change. This is like the law of conservation of energy, where we can neither create nor destroy energy, just change it from one form to another. We must always keep total value. Let's look closer at the 2 actions in this category. I think the big-small action is very powerful and useful because it helped me connect many steps in pre-algebra problems and in algebra equations. Big-small is like squeezing a water balloon. One part gets bigger while the other part gets smaller, but the total amount of water stays the same. This action works on only one side of an equation or without an equation. It applies 2 opposite effects to one object. A simple example is 2 plus 7. What if you wanted the 2 to decrease to 1? Then you need a counter change and increase the 7 to 8. The total value of the problem is always 9, even though the partial values change. 9 minus 6 becomes 8 minus 5 because the 9 becomes smaller by 1 while the negative 6 becomes larger by 1. Common examples include percents. 1 becomes 2 places bigger to become 100, but then it is countered with the percent sign, which has the effect of dividing by 100, which makes the number 2 places smaller. Point 50 becomes 2 places bigger to 50, but attaching the percent counters it with 2 places smaller. 5,000 becomes 2 places smaller to 50, but removing the percent counters it with 2 places bigger. Scientific notation becomes less intimidating with big small. 230 becomes 2 places smaller to 2.3. The 7 becomes 2 powers bigger to 9. Point 4 needs to become 4. Since the number got bigger, the power must get smaller. 1 power smaller than the invisible 1 is 0. 68 becomes 1 place smaller to 6.8. The 5 power gets 1 bigger to 6. The pattern continues with units. Yards become 3 times smaller to feet, so the 5 becomes 3 times bigger to 15. Meters gets 1,000 times bigger to kilometers, so the 8,000 gets 1,000 times smaller to 8. Days get 24 times smaller to hours, so 2 becomes 24 times bigger to 48. Polynomials also get bigger smaller by looking at the inside versus outside. The 8 on the outside gets twice as small to 4, so the inside and everything in it gets twice as big. Do the multiplying and you will see the overall value of 16y plus 24 never changed. Distributing parentheses is a big small action when you realize that there are invisible parentheses and 1 in the answer. This is also an example of the show action. The outside got 3 times smaller while the inside got 3 times bigger. Common factoring is also big small. Making the inside smaller by a factor of 2 makes the outside bigger by a factor of 2. Now let's look at the type of problem we all love to hate, fractions. They have a division part, which means reverse multiplication, which means we reverse a reverse. The mud action explains all this. 4/6, or 4 over 6, means I have 4 out of 6 pieces of pie. I must keep total value and guard my dessert plate from bullies trying to rob me of pie. So if for some reason I wanted my pie served in only 2 pieces, do I want bigger or smaller sized pieces? Well, I want them bigger, so the bottom number must be smaller. Dividing by a smaller number actually makes bigger pieces and gives me back my value, and it is value that we must keep. 2 out of 12 pieces of pie is a lot less than 2 out of 3. Your hungry stomach will tell you that. Notice again that big small does not say there must be a bigger number and a smaller number, nor that you must always multiply or always divide or one of each. You multiply or divide numbers bigger or smaller to make one value bigger and the other smaller. One thing will be plain, then you figure out the other part. Putting colt and big small together tells us why and how we must make common denominators. 4 and 3 need to be multiplied to 12. The question is, what do we do to the top? Making a bigger number on the bottom just made the fraction smaller. Therefore, I need to make the top bigger. Multiplying, not dividing, achieves that. Many students and teachers think only of the numbers instead of the total value. That is why they try to memorize their way through different problems and then confuse themselves. Learning how division has the reverse effect of multiplying, then looking at the bigger, smaller effects will tie all these problems together. With the time we have left, let's look at equations which use balance and other actions together. Mixing in a little experience, we can devise a way to solve all single variable, single degree equations using the same 6 steps in the same order. I have taught from a variety of algebra textbooks, and so far I have not run into a case that cannot be solved using what I call the FA method. Start with step F and fill parentheses, flip complex fractions, and/or figure functions. Notice that all of them use big small. Do this step as many times as needed before moving on. In this case, we figure the function with the exponent because it's inside, and then we fill parentheses. Next, we move to E, a big small step also, and see if we need to do anything. Indeed, we need to eliminate decimals by multiplying everything both sides by the greatest number of places. In this case, it's one place, which is 10 to the 1, or 10. The previous step set us up to figure the correct number of places. Step D tells us to decouple the plain numbers from the variable terms. So we switch sides, switch signs to make letters left and numbers right. Just move the terms and change the signs without writing out the error-prone intermediate combining on each side. This is part of the balance action. Notice that we check the problem for each lettered step. We might skip a step if not needed, but never do them out of order. Step C has us combine like terms, colt, on each side because step D prepared us for this step. Step B breaks the variable term by dividing both sides by the coefficient, balance action. The coefficient will always be a whole number because of step E. Finally, step A gives us an answer which we can check, reduce, or round per instructions. Also, by substituting it back into any step of the equation, we can see that the total value of both sides always equaled each other. These steps in this order keep students from accidentally making the equation harder and then losing themselves in their own complexity. FA has solved every problem I have encountered, but if you can find one that it can't, I would like to know. There is a similar FA method for quadratic equations. Hopefully, this small sample of using actions has begun to persuade you of the existence and power of math patterns which apply to all curriculums. I have no doubts that the 9 actions can be improved, but my point is that we can help students organize their thinking. The hundreds of different kinds of math problems can become familiar to them. We can keep repeating and forgetting and reteaching and failing a conglomeration of rules and exceptions, or we can use patterns to make the unknown known and reduce the fear and stress. Let's rethink our teaching methods and help our students and teachers succeed.